Hi Calc 2 students. Today we're going to be covering our first basic integration technique outside of our just standard integration identities called U substitution. So to understand what U substitution is, I think it's helpful if we kind of go back to the derivative. So if we go back to the concept of taking a derivative of a function such as cosine of x squared, we notice that what is unique about this function is that it's kind of got an inner function of x squared and an outer function of cosine of x. So you see how we have a composition of functions where our inner function, x squared, is inside and our outer function, cosine of x, is very visually on the outside. When we take the derivative of such a function, we are used to applying the chain rule. So when we take the derivative, first what we do is we take the derivative of the outer function, cosine of x. The derivative of that would be, derivative of cosine is negative sine. So negative sine, and then x squared. And then chaining on the derivative of the inner function, which is 2x. So then if we go ahead and look at how we would undo that derivative, we have the integration process, and the process that we would use to undo that is going to be what we're learning called U sub. So in order to integrate this function, what we would do is we would notice that we have a clear derivative of the inner function, and then go backwards from sine to get to the cosine. Okay. So that's going to be the basic concept of what we're learning. Let's jump in and do some examples to figure out the specifics of this. So moving on to our exercises, let's take a look at these functions and practice that strategy of finding a clear inner and outer function. So looking at our first example, we have the integral of x to the fourth cosine of x to the fifth dx. So I'm going to go ahead and identify my inner and outer function. Let's take a look. It looks like the inner function here would be x to the fifth. And then I see a derivative of x to the fifth happening here. I almost see exactly the derivative, but I see just the main function of x part, x to the fourth. If you remember the derivative of x to the fifth, it would be 5x to the fourth. So if I just do a quick touch up on this integral, if I add the 5 in, okay, and if I add the 5 on the inside, I need to also multiply by a constant of 1/5 on the outside to correct it. So I'm going to touch this integral up. I have 5x to the fourth cosine x to the fifth dx, and I got that 1/5 hanging out front. This is a correction factor is what I usually call it. And now we see we have exactly what we wanted. We have an inner function and we have the derivative of the inner function. So I can go ahead and identify that my u is x to the fifth, my du is 5x to the fourth, and rewrite this integral as cosine of u. And some people ask, well, what do we do with the dx? The dx gets chained on along with the du. So, and the 1/5 is hanging out front. So the integral of cosine will give us a sine of u with the 1/5 out front, plus our integration constant, and replacing our u, we get 1/5 sine of x to the fifth plus c. Okay, now we're going to do a quick check because this is our first exercise. Let's make sure that when we take the derivative, we get back to the original. Derivative of sine x to the fifth would be cosine x to the fifth, chain on the derivative, 5x to the fourth, and that gets us back to our original with the correction factor of a fifth out front. Okay, so let's move on to exercise number 2. Taking a look at this one, it looks like I have an interesting notation, which is very common with trig functions. I'm going to go ahead and pull the 15 out front because it's vaguely distracting, and realize that when you see trig functions, what's common is for people to put the exponent between the letters and the argument x. So you can think of this as actually being like sine x squared. Some students, it really helps to rewrite it that way, even though it's not the most correct notation, just to visualize what is really our inner and outer function. I see we have an inner function of sine x, and the derivative of that is right here, cosine x dx. So I see that this integral is all ready to go. I have my u of sine x, and I have my du, which is derivative of sine is cosine x dx. So I can immediately rewrite this integral without doing any correction factor. We have u squared du, and we integrate. When you integrate, we're remembering our power rule, so we up the power by 1, multiply by that 1/3 out front. You still have the 15, and our integration constant, we're not going to forget that. So this becomes 5, replacing our u again with our function of x. So we get 5 sine x cubed. And remember, the most correct way to write that is to put the exponent between the letters in the argument and our integration constant, plus c. So when we were to take the derivative of this, we would get 15 sine squared x, chain on the derivative of sine x, which is cosine x. And we're correct. So every time we integrate, one thing to mark down in your notes is that we can always check by taking the derivative. So if you're asking yourself whether you did something correctly, your derivative should match with your original expression inside the integral. That's how you know you did your integral correct. Okay, moving on, let's go to exercise 3. We're computing the integral of e to the x over e to the x minus 7 with respect to x. So this one's a little more challenging. When we look at this, we see a couple e to the x's, and it's kind of a little bit harder to see your inner and outer function. But one thing that I think helps is to notice that when we're trying to do u substitution, you want to take as much as possible for your inner function. So if I look at this denominator here, if I take the whole denominator, e to the x minus 7, then I notice the derivative of that is here, e to the x dx. So if I make my u e to the x minus 7, taking as much as I possibly can of that denominator, and then I take the derivative of that, derivative of e to the x, the derivative of a constant is 0. I notice that I can rewrite this integral as 1 over u du. Okay, and some people will kind of think, well, why wouldn't I make e to the x my u? If you make e to the x your u, look at how this gets rewritten. You have du is e to the x, so when you rewrite this, you would get, you have u up top, or I guess you would have to make the top du. So you'd have 1 over u minus 7 du. Okay, so slightly harder integral, but you're not technically incorrect. It's just going to be easier if we make our u as much as possible. Okay, so this is another option, and we'll just go ahead and flag that. If you wanted to try doing it this other way just to see how it would go, you can do that on your own paper. We're going to go ahead and go with the strategy that is probably the easiest, which is taking your u to be e to the x minus 7. So computing this integral of 1 over u is one of our basic integrals, and you might remember that is ln of the absolute value of u is the antiderivative there. And then when we replace our u, we get ln of e to the x minus 7 plus c. And again, we can check by taking the derivative to see if we did it correctly. Okay, so these are getting spicier quickly. In exercise 4, we're going to compute the integral of the square root of ln x over 5x with respect to x. Okay, when I look at this function, I see kind of an obvious inner function that jumps out to me. To me, the inner function here is going to be whatever is inside the square root, because if you see anything other than a simple x inside a square root, that's a very obvious composition. So my instinct is going to be to take u to be ln x. If I make u to be ln x, then my du would be 1 over x dx. And let's see if we have it. I see that we do. Here's my 1 over x dx. Okay, so I have an extra constant of 5 in the denominator. So if I rewrite this, if I just pull that 5 out, you can do that with constants. You can never do it with x's, but you can pull out a constant from an integral. Then I have square root of, there's my u inside the square root, and then 1 over x dx is my du. Take a moment to see that you understand how we rewrote that integral, noticing that because the x is in the denominator, it's really a 1 over x, which got absorbed into this du. Okay, so now we're ready to integrate. I'm going to go ahead and remind you guys of probably the easiest trick for integrating square roots, short of just memory, which is a square root can also be written as an exponent of a half. And if you have the exponent of a half, the rule is you up the power by 1. So adding 2 over 2 gives us 3 halves, and you multiply by the reciprocal out front. So we've got a fifth times 2/3, u to the 3 halves, which gives us 2 over 15. And our u was ln x, and that's raised to the power of 3 halves. And then don't forget your integration constant. There we go. Let's take a look at some more examples. Let's take a look at this one. The integral of sine of square root of x over square root of x. Okay, I see an obvious candidate for you. Let's see if you guys see it as well. If we were to include sine of anything in our u, the du would need to include a cosine, and obviously this integral doesn't contain a cosine. So we can't make our u contain the sine, which means that probably the most we could take for our u would be square root of x. Then the question is going to be, when we make our u root x, do we see our derivative? So let's rewrite that as x to the 1/2. When we take the derivative, we get du is 1/2 x to the subtract 1. 1/2 minus 1 is -1/2. So if I rewrote this as a radical expression, I would have 1 over 2 root x. Oh, and let's check it. We've got, here is our u. Here's our du right there, 1 over square root x. So the only thing we need is that factor of a half. So I'm going to go ahead and correct this integral by multiplying by a half on the inside. Okay, and then multiply by the reciprocal of a half on the outside for your correction factor. Okay, take a moment to look at that and just understand that when you multiply by a constant on the inside of the integral, that changes the integral unless you also multiply by that correction factor out front as well. And some students ask me, is it necessary to actually write this step out? And the answer is, in the long run, no. A lot of you guys are going to be so good at integration by the end of this course that you might not need to do that. But in the beginning, I'm expecting that everyone is very novice at integrating, and they are very likely to need this step. So I personally err on the side of always showing it to you guys. And I certainly have a preference that if students are at all on the fence, they go ahead and actually go through the work to write out the correction factor and don't just try and do that in your head. Okay, so now that I have this corrected, I can see my u and my du. I have 2, integral of sine of u, and then du. Okay, integrating that, we get 2. The integral of sine is negative cosine of u. Okay, rewriting this, we have negative 2 cosine, and u was root x. And then, not forgetting that, plus c. There we go. Okay, so moving on, let's go ahead and go to exercise 6. We're taking the integral of 7x to the 5th over 4x to the 6th minus 15 quantity to the 4th with respect to x. Okay, so a lot going on here. I would like to just point out that whenever you see rational functions, which means you have a polynomial in the numerator and a polynomial in the denominator, there's going to be only certain strategies that will ever help to integrate them. And u sub is the first one we're always going to try. So right away, I see polynomial on the top, polynomial on the bottom. I'm really hoping that I can find a u sub. So when I look at this, kind of the two candidates that I see for a u would be either we could take the x to the 5th in the numerator, or we could take that entire denominator of 4x to the 6th minus 15. But I want to take as much as possible. And to me, I think the first choice I would try would be taking everything that's being raised to the 4th power, because that would clean this integral up quite a bit. So I'm going to try and take that whole 4x to the 6th minus 15 and see if I can find that du in here. Here's the du. 24x to the 5th, derivative of negative 15 being 0. Dx, chain it on. Okay, now I'm going to look and see, is there any way that I can, that I have my enough of the du that a simple multiplying by a constant will correct it? And I notice I have my x to the 5th dx sitting up top, which is good. That means I can use this u. Some people are going to notice, well, hey, you have this 7 here. What are we going to do about that? Because I can't think of anything to multiply the 7 by that's going to get me a 24. And my response to that would be, doesn't matter, because we can fix the constant part. So what I'm going to do to fix this is I'm going to pull that 7 out to the front, not worry about it. What do I want to have? I want to have a 24 in the numerator. So all I have to do is correct that by multiplying by over 24, and we're good. So there's my 24 that I wanted. And now I see exactly the du. Again, this step of rewriting it is optional, but I think very helpful. Strongly recommend. So now I'm ready to go ahead and integrate. I have 7 over 24, and rewriting this, I have 1 over u to the 4th du. And so that's the same as if I rewrite this as u to the negative 4. That helps me see the power rule a little bit better. So remember, when you integrate with the power rule, you up the power by 1. So negative 3 multiplied by the reciprocal. So the reciprocal of negative 3 is going to be negative 1/3. Just kind of I always do the reverse in my head just to check with these fractions. Yep, looks good. And then rewrite this without the u's. So we have negative 7 over 72 out front. And then u to the negative 3 is 4x to the 6th minus 15 to negative 3 plus c. Okay, and remember, guys, using u is a tool. Using u is a tool. What that means is when you think about computing these integrals, your answer should not contain a u, because a u is a tool that you used rather than something that a variable that has true meaning within the problem. So if you go ahead and left me with something that had u, like the second to last line, you're not really answering the question of what you were supposed to compute. This expression has x's. Your answer also needs to be in terms of x. And this goes for any change of variable because we will do several other kinds as well. So it's always just a good habit to, from the beginning, make sure your variables are matching with the original. Okay, so moving on. Let's take a look at example 7. So this is computing the integral of x over quantity x minus 1 squared with respect to x. Okay, 2 candidates, and going along with that trend of making your u as much as possible, my inclination is I really want to choose my u to be x minus 1. If I put the squared in there with it, it'll make a mess. It won't, I don't have the, actually, maybe we can. Let's go ahead and see, because there's a chance. If I go ahead and try and make my u x minus 1 squared, when I take the derivative, I would get 2 times x minus 1 to the power of 1, chain on the derivative inside of 1. So, okay, that's actually not that bad. But that minus 2 is throwing me because I'm allowed to multiply by a constant, but I am not allowed to just like add a minus 2 in here. You can't minus 2 and then add 2, literally. So just like many of you guys are going to do, I made a guess. Didn't quite work out. Not like how I thought, at least. So let's try another guess for you. Let's go ahead and make the u just the x minus 1 part. Okay, so let's not include the squared part. When I make the u x minus 1, I see the derivative of that is going to be 1 dx. Okay, that I have made for me. So I can go ahead and do this u substitution, and this is going to be one of those instances where at first a u substitution might look like, oh, you know, this integral isn't getting easier immediately to the eye, but I urge you to just bear with me here. So if we go ahead and make this u substitution, we notice that in the numerator, we have a little extra in terms of x. We have an x in the numerator, and so when we rewrite it, it's not going to be just as simple as writing a du. So when I rewrite it, I notice that x will equal u plus 1. If we look at what u equals, x has to equal u plus 1. So that denominator is going to become u plus 1. The denominator is going to become u squared. Then we have that, the du there. Yep. Okay, so look at how we rewrote that. Just once again, here is my u. Here is my du. And then I have extra. That x is not included as part of the du, so I got to rewrite it in terms of u. We've made our change of variables. Now I'm going to rewrite this in the way, like this integral doesn't look nice. I agree with you. But if you think about how fractions work, look at what it becomes when you split that fraction up. So we're still just doing algebra here, nothing fishy. This integral looks a whole lot easier to me. This looks like integral of 1 over u plus 1 over u squared du. You can compute those separately, like so. The first derivative, super easy. The second derivative, also super easy. So reminding yourself that this is actually equal to u to the negative 2. We have a power rule and a simple identity. So we have ln of u from the first integral, and then upping the power by 1, we get u to the negative 1 multiplied by the reciprocal, negative u to the negative 1. Okay, and then rewriting this expression with our original variable, ln of x minus 1 minus 1 over x minus 1. Don't forget about the integration constant. Pretty cool, huh? You're probably like, that is far from an appropriate use of the word cool. Cool should really not ever be applied to math. Maybe you're thinking that, maybe not, but to me, that's kind of cool. Okay, so let's take a look at the next and final example. Okay, so this is another one where it looks like either way, like no matter how we choose our u, there's going to be certain ways that aren't helpful to us. And this might be a trial and error situation. To me, I see a square root and my instinct is going to be take whatever is inside the square root because that always makes the integration easier if you can do that. So my first guess is going to be to make u equal to 2x minus 1, which would make du 2 dx. Okay, and when I rewrite this, what I notice is I have another little extra x, so that might be helpful to realize that x would be u plus 1 over 2. Okay. And how am I doing that? I'm doing algebra, so I'm adding the 1 to both sides and then dividing by 2. I've done a lot of algebra in my day, and you guys probably have too, though not quite as much as me. So you guys might need to actually kind of write those steps out in the beginning, and then as your brain gets a little bit more warmed up to integration, you might not need to do that. So okay, we got u plus 1 over 2 is our x. Rewriting this integral, we have u plus 1 over 2, and then the square root of u. Hold on a second. I don't have that 2 that I need. So if I multiply by a 2 on the inside, I'm actually going to go ahead and erase this step. It was a little premature writing that. I need to add that factor of 2 in. So multiplying by a 2 on the inside, we need to multiply by a half. We have 2x, root x, 2x minus 1 dx. Now we can replace our u's, so we have a half. And here is our du, the dx, and the 2. So rewriting this, we have u plus 1 over 2 and root u du. Okay, so I'm going to pull that constant of a half out, so give us a quarter. And then I have u plus 1. This is multiplied by the square root u. Okay, it's important to remember because really this square root u distributes. And I have u to the 1 times root u gives me u to the 3 halves. Okay. So if this is 2 over 2, and this is u to the 1 over 2, remember the powers add, and then plus u to the 1 half du. Power rule, so we have a quarter times up the power by 1, you get 5 halves, multiply by the reciprocal. Up the power by 1, you get 3 halves, multiply by the reciprocal. And that a quarter is applied to everything because it's out front the integral. So now I can go in and substitute back in my expression with x. My u is equal to 2x minus 1, so this becomes 1 over 10. And then you get 2x minus 1 to the 5 halves plus 1 over 6, 2x minus 1 to the 3 halves. Okay, and I did some arithmetic in my head there. I'm assuming that as I make these videos, you guys are going to be pausing if you need to, watching me in half speed if you need to, slowing me down just a little bit instead of editing in just the dead space that you would then have to fast forward through. So that's my take. What did I forget? The integration constant. There we go. So this might be one where you might want to pause and just kind of, refresh yourself on those fractions, which, while basic, do get the best of a lot of us. It's frequently the small stuff that gets us. Okay, This was our introduction to U substitution, and I'll see you guys next time for other integration techniques.